Introduction to Statistics. Statistics is a scientific discipline concerned with the collection, organization, analysis, interpretation, and presentation of data. It provides the tools and methods necessary to understand variability, make informed decisions, and draw reliable conclusions from empirical evidence. This field is fundamental in nearly every domain, from scientific research and business analytics to public policy and healthcare, enabling us to quantify uncertainty and uncover patterns. Understanding statistics is crucial for anyone working with data, as it underpins the validity and reliability of findings, guiding strategic planning and problem-solving. The importance of statistics extends to its ability to transform raw data into actionable insights, helping to predict future trends and evaluate the effectiveness of interventions. It allows for the rigorous testing of hypotheses, ensuring that conclusions are not merely anecdotal, but are supported by quantifiable evidence. Through statistical analysis, we can identify correlations, understand cause and effect relationships, and model complex phenomena. This foundational knowledge empowers individuals to critically assess information and contribute meaningfully to data-driven environments. Types of statistics. Statistics is broadly categorized into two main types: descriptive statistics and inferential statistics. Descriptive statistics involves methods for organizing, summarizing, and presenting data in an informative way. This includes calculating measures like the mean, median, mode, range, and standard deviation, as well as creating visual representations such as histograms and pie charts. The primary goal of descriptive statistics is to describe the characteristics of a dataset without making generalizations beyond that specific data. It helps to simplify large amounts of data into more manageable and understandable forms, providing a clear snapshot of the information. Inferential statistics, on the other hand, uses data from a sample to make generalizations or draw conclusions about a larger population. This involves techniques like hypothesis testing, confidence intervals, and regression analysis. The core idea is to infer properties of a population based on observations from a subset of that population, accounting for the inherent uncertainty of sampling. Inferential statistics allows researchers to test theories, predict future outcomes, and determine the significance of observed differences or relationships. It moves beyond mere description to provide insights into broader patterns and relationships, forming the basis for evidence-based decision-making. Data collection methods. Effective data collection is the cornerstone of any sound statistical analysis, as the quality of the data directly impacts the validity of the conclusions. Data can be broadly classified into primary and secondary sources. Primary data is collected directly by the researcher for a specific purpose, often through surveys, experiments, observations, or interviews. This method allows for greater control over the data's relevance and accuracy, tailored precisely to the research questions at hand. However, it can be time-consuming and resource-intensive, requiring careful planning and execution to avoid biases and errors. Secondary data, conversely, is data that has already been collected by someone else for a different purpose and is readily available from existing sources. Examples include government publications, academic journals, company reports, and online databases. Utilizing secondary data is often more cost-effective and less time-consuming than collecting primary data, providing access to large datasets that might otherwise be inaccessible. The challenge lies in ensuring the data's relevance, reliability, and accuracy for the current research, as it was not originally gathered with the specific research objectives in mind. Critical evaluation of secondary sources is therefore paramount. Sampling techniques. Sampling techniques are crucial for selecting a representative subset of a population when it is impractical or impossible to study the entire group. These methods are broadly divided into probability sampling and non-probability sampling. Probability sampling methods ensure that every element in the population has a known, non-zero chance of being selected, which allows for statistical inference about the population. Common types include simple random sampling, where each individual has an equal chance, stratified sampling, which divides the population into subgroups before random selection, and cluster sampling, where entire groups are randomly selected. These methods are preferred for their ability to produce unbiased estimates and generalize findings. Non-probability sampling methods do not involve random selection, meaning that some elements of the population have no chance of being selected, and the probability of selection cannot be determined. These methods are often used in exploratory research, or when probability sampling is not feasible due to time, cost, or logistical constraints. Examples include convenience sampling, where participants are chosen based on their easy accessibility, quota sampling, which aims to match the sample's proportions to the population's characteristics, and snowball sampling, where initial participants refer others. While useful for specific contexts, findings from non-probability samples typically cannot be generalized to the larger population with statistical confidence. Types of data. Data can be broadly classified into qualitative and quantitative types, each requiring different statistical approaches. Qualitative data, also known as categorical data, describes characteristics or categories that cannot be measured numerically. Examples include gender, hair color, types of cars, or satisfaction levels. Examples: satisfied, neutral, dissatisfied. This type of data is often collected through observations, interviews, or open-ended survey questions, providing rich, descriptive insights. While it helps in understanding underlying reasons and motivations, qualitative data typically requires non-parametric statistical methods for analysis, focusing on frequencies and proportions rather than numerical calculations. Quantitative data, conversely, consists of numerical values that can be measured or counted. This type of data can be further divided into discrete and continuous data. Discrete data results from counting and can only take specific, distinct values, such as the number of students in a class or the number of defects in a product. Continuous data, on the other hand, can take any value within a given range, often resulting from measurement, such as height, weight, or temperature. Quantitative data is amenable to a wide range of parametric statistical analyses, including calculations of means, standard deviations, and regression models, providing precise and measurable insights into phenomena. Scales of measurement. Understanding the scales of measurement is fundamental in statistics, as it dictates the types of statistical analyses that can be appropriately applied to data. There are 4 primary scales: nominal, ordinal, interval, and ratio. Nominal scale data are purely categorical, used for labeling variables without any quantitative value or order. Examples include gender, marital status, or types of fruit. For nominal data, one can only count frequencies and proportions, and modes are the only measure of central tendency applicable. No mathematical operations beyond counting are meaningful for this level of measurement. Ordinal scale data also categorizes variables, but with a meaningful order or rank, though the differences between ranks are not necessarily equal or measurable. Examples include satisfaction ratings, e.g., poor, fair, good, excellent, educational levels, or military ranks. While we know that excellent is better than good, we cannot quantify the exact difference between them. Medians and modes can be calculated for ordinal data, but means are generally inappropriate. The inherent order allows for comparisons of relative position, but not magnitude of difference. Interval scale data has ordered categories with equal intervals between them, but it lacks a true 0 point. Temperature measured in Celsius or Fahrenheit is a classic example. The difference between 20 degrees Celsius and 30 degrees Celsius is the same as between 30 degrees and 40 degrees. But 0 degrees Celsius does not mean an absence of temperature. With interval data, means, medians, and modes can all be calculated, and arithmetic operations like addition and subtraction are meaningful. However, ratio comparisons, e.g., twice as hot, are not valid because of the arbitrary 0 point. Ratio scale data is the most informative level of measurement, possessing all the characteristics of interval data but with a true, meaningful 0 point. This 0 point indicates the complete absence of the measured quantity. Examples include height, weight, age, income, or the number of items sold. With ratio data, all statistical analyses are applicable, including ratios and multiplications, making statements like twice as heavy or half the age meaningful. This scale allows for the most comprehensive statistical treatment and interpretation. Descriptive statistics. Central tendency. Measures of central tendency are statistical values that represent the center or typical value of a dataset. The three most common measures are the mean, median, and mode, each providing a different perspective on the data's central point. The mean, often referred to as the average, is calculated by summing all values in a dataset and dividing by the number of values. It is highly sensitive to outliers, meaning extreme values can significantly skew its representation of the center. The mean is best used with interval or ratio data that is symmetrically distributed, providing a precise numerical average. The median is the middle value in a dataset when the values are arranged in ascending or descending order. If there is an even number of observations, the median is the average of the two middle values. Unlike the mean, the median is robust to outliers, making it a more appropriate measure for skewed distributions or ordinal data. It represents the point at which half of the data falls below and half falls above, providing a good sense of the typical value without being unduly influenced by extremes. The mode is the value that appears most frequently in a dataset. A dataset can have one mode, unimodal, multiple modes, multimodal, or no mode if all values appear with the same frequency. The mode is the only measure of central tendency that can be used with nominal data, and it is useful for identifying the most common category or value. It provides insight into the most popular or prevalent observation within the data. Descriptive statistics. Dispersion measures of dispersion, also known as measures of variability, describe how spread out or scattered the data points are in a dataset. While central tendency tells us about the typical value, dispersion tells us about the consistency or variability around that central point. The range is the simplest measure of dispersion, calculated as the difference between the maximum and minimum values in a dataset. It provides a quick, rough estimate of spread, but is highly sensitive to outliers and does not account for the distribution of values between the extremes. It is useful for a quick overview, but lacks robustness. Variance and standard deviation are more sophisticated and widely used measures of dispersion. Variance measures the average of the squared differences from the mean, providing a numerical value indicating how far individual data points are from the average. The standard deviation is the square root of the variance, expressed in the same units as the original data, making it more interpretable. A small standard deviation indicates that data points are clustered closely around the mean, while a large standard deviation suggests that data points are widely spread out. These measures are crucial for understanding the reliability of the mean as a representative value and for comparing the variability between different datasets. The interquartile range, IQR, is another robust measure of dispersion, calculated as the difference between the third quartile, Q3, and the first quartile, Q1. It represents the spread of the middle 50% of the data, making it less sensitive to outliers than the range. The IQR is particularly useful for skewed distributions and for identifying potential outliers in a dataset, providing a clear picture of the central spread. Data visualization is the graphical representation of information and data, using visual elements like charts, graphs, and maps to see and understand trends, outliers, and patterns in data. It transforms complex datasets into accessible and understandable visual forms, making it easier to communicate insights and findings to a broad audience. Effective data visualization is crucial for exploratory data analysis, helping researchers identify relationships and anomalies that might be missed in raw numerical data. It also plays a vital role in presenting results clearly and persuasively, enhancing comprehension and engagement. Various types of charts serve different visualization purposes. Histograms are used to display the distribution of a continuous variable, showing the frequency of data points within specific intervals. Bar charts compare categorical data, illustrating the frequency or proportion of different categories. Pie charts represent parts of a whole, showing the percentage distribution of categories within a single variable. Box plots are excellent for visualizing the distribution of numerical data and identifying outliers, summarizing key statistics like median, quartiles, and range. Scatter plots are used to display the relationship between two continuous variables, helping to identify correlations and patterns. Each visualization tool is chosen based on the type of data and the specific insights one wishes to convey, ensuring clarity and accuracy in data interpretation. Probability theory fundamentals. Probability theory is the mathematical framework for quantifying uncertainty and randomness, forming the bedrock of inferential statistics. It deals with the likelihood of events occurring, providing a systematic way to analyze situations where outcomes are not certain. Key concepts include experiments, which are processes with uncertain outcomes, which are the results of an experiment, and events, which are specific collections of outcomes. The probability of an event is a numerical value between 0 and 1, where 0 indicates impossibility and 1 indicates certainty. Understanding these fundamental concepts is essential for making predictions and drawing conclusions from data that inherently involves chance. The rules of probability govern how probabilities are combined and manipulated. The addition rule helps calculate the probability of either one or both of two events occurring, particularly useful for mutually exclusive events where the occurrence of one precludes the other. The multiplication rule determines the probability of two or more events occurring in sequence, distinguishing between independent events, where one does not affect the other, and dependent events, where one's outcome influences the other. Conditional probability, a crucial concept, measures the probability of an event occurring given that another event has already occurred. These rules provide the logical structure for analyzing complex probabilistic scenarios, enabling statisticians to model and predict outcomes in various real-world situations. Probability distributions. A probability distribution describes all the possible values a random variable can take and how often they occur. These distributions are fundamental for modeling real-world phenomena and making predictions. They are broadly classified into discrete and continuous distributions. Discrete probability distributions deal with variables that can only take a finite or countably infinite number of distinct values, typically integers. Examples include the number of heads in coin flips or the number of defects in a batch of products. These distributions are often visualized using bar graphs, where the height of each bar represents the probability of a specific outcome. Understanding discrete distributions is crucial for analyzing count data and events with distinct, countable results. The binomial distribution models the number of successes in a fixed number of independent Bernoulli trials, each with the same probability of success. It is widely used in quality control, genetics, and polling. The Poisson distribution, on the other hand, models the number of events occurring in a fixed interval of time or space, given a constant average rate. It is applicable to rare events, such as the number of calls received by a call center in an hour, or the number of accidents on a road segment. Continuous probability distributions apply to variables that can take any value within a given range, such as height, weight, or temperature. These distributions are represented by probability density functions, PDFs, where the area under the curve over an interval gives the probability. The normal distribution, often called the bell curve, is the most important continuous distribution due to its prevalence in natural and social sciences and its role in the central limit theorem. It is characterized by its mean and standard deviation and its symmetric shape. The exponential distribution models the time until an event occurs in a Poisson process, such as the lifespan of an electronic component or the waiting time in a queue. These continuous distributions are vital for analyzing measured data and understanding phenomena that vary smoothly over a range of values. Sampling distributions. A sampling distribution is the probability distribution of a statistic obtained from a large number of samples drawn from a specific population. It describes the behavior of a sample statistic, like the sample mean or sample proportion, if we were to take many samples of the same size from the same population. Understanding sampling distributions is crucial because it allows us to quantify the uncertainty associated with using sample statistics to estimate population parameters. It forms the bridge between descriptive statistics and inferential statistics, providing the theoretical basis for hypothesis testing and confidence intervals. Without sampling distributions, it would be impossible to determine how reliable our sample estimates are. The central limit theorem, CLT, is a cornerstone of statistical theory, stating that the sampling distribution of the sample mean will be approximately normally distributed, regardless of the shape of the population distribution, provided the sample size is sufficiently large. This remarkable theorem holds true even if the original population is not normally distributed, making it incredibly powerful for statistical inference. As the sample size increases, the sampling distribution of the mean becomes narrower, indicating that the sample means are clustering more closely around the true population mean. This property allows us to use the normal distribution to construct confidence intervals and perform hypothesis tests on population means, even when we don't know the population's original distribution. The sampling distribution of the mean, specifically, helps us understand how much sample means are expected to vary from one sample to another, providing a measure of precision for our estimates. Hypothesis testing. Introduction. Hypothesis testing is a formal statistical procedure used to make decisions about a population parameter based on sample data. It involves formulating two competing hypotheses, the null hypothesis, H0, and the alternative hypothesis, HA, or H1. The null hypothesis typically represents a statement of no effect, no difference, or no relationship, often reflecting the status quo or a commonly accepted belief. The alternative hypothesis is the statement that the researcher is trying to prove, suggesting an effect, a difference, or a relationship. The goal of hypothesis testing is to determine whether there is enough evidence from the sample data to reject the null hypothesis in favor of the alternative. This structured approach ensures that conclusions are drawn systematically and objectively, minimizing the risk of erroneous claims. In the process of hypothesis testing, two types of errors can occur. A type 1 error happens when we incorrectly reject a true null hypothesis. This is often referred to as a false positive, and its probability is denoted by alpha, the significance level. A common significance level is 0.05, meaning there is a 5% chance of making a type 1 error. A type 2 error occurs when we fail to reject a false null hypothesis, often called a false negative. Its probability is denoted by beta, B. There is an inverse relationship between type 1 and type 2 errors. Reducing one often increases the other. The power of a test, 1 minus beta, is the probability of correctly rejecting a false null hypothesis. Understanding these errors is critical for interpreting the results of a hypothesis test and for making informed decisions about the trade-offs between different types of mistakes. Hypothesis testing. Z-tests and t-tests. Z-tests and t-tests are two of the most common statistical tests used to compare means and make inferences about population parameters. A Z-test is typically used when the population standard deviation is known, or when the sample size is large, generally n greater than 30, allowing the sample standard deviation to be a good estimate of the population standard deviation. It compares a sample mean to a hypothesized population mean, or compares two sample means, assuming the data is normally distributed. The Z statistic measures how many standard deviations an observation or a sample mean is from the population mean, providing a standardized way to assess significance. Its application relies on the central limit theorem for large samples, making it powerful in many scenarios. A t-test is used when the population standard deviation is unknown and the sample size is small, typically n less than 30. In such cases, the sample standard deviation is used to estimate the population standard deviation, and the t-distribution is used instead of the normal distribution. The t-distribution is similar to the normal distribution, but has heavier tails, accounting for the increased uncertainty due to the smaller sample size. There are various types of t-tests, including one-sample t-tests, comparing a sample mean to a known population mean, independent samples t-tests, comparing means of two independent groups, and paired samples t-tests, comparing means of two related groups. Choosing between a z-test and a t-test depends critically on whether the population standard deviation is known and the size of the sample. Ensuring the appropriate statistical assumptions are met for valid inference. Hypothesis testing, chi-square tests. Chi-square tests are non-parametric statistical tests, primarily used to analyze categorical data. They are particularly useful for determining if there is a significant association between two categorical variables, or if an observed frequency distribution differs significantly from an expected distribution. Unlike z-tests and t-tests, which focus on means of numerical data, chi-square tests work with counts and proportions, making them indispensable for research involving qualitative data. The test statistic measures the discrepancy between observed frequencies and expected frequencies, providing a basis for evaluating hypotheses about categorical relationships. These tests are robust and widely applied in social sciences, market research, and biology. The two main types of chi-square tests are the goodness of fit test and the test of independence. The chi-square goodness of fit test is used to determine whether an observed frequency distribution for a single categorical variable differs significantly from an expected distribution. For example, it can test if customer preferences for different product colors are uniformly distributed or if they follow a specific historical pattern. The chi-square test of independence, on the other hand, is used to examine the relationship between two categorical variables. It assesses whether there is a statistically significant association between the variables, or if they are independent. For instance, it can determine if there is a relationship between gender and political affiliation, or between educational level and job satisfaction. Both tests rely on the chi-square distribution to calculate p-values and make decisions about the null hypothesis, providing powerful tools for analyzing categorical data patterns. Analysis of variance, ANOVA. Analysis of variance, ANOVA, is a statistical technique used to compare the means of three or more independent groups to determine if at least one group mean is significantly different from the others. While multiple t-tests could theoretically be used for this purpose, ANOVA is preferred because it controls the type 1 error rate, the probability of falsely rejecting a true null hypothesis that would inflate with repeated t-tests. ANOVA partitions the total variability in a dataset into different sources, variability between groups, and variability within groups. By comparing these variances, ANOVA determines if the differences observed between group means are likely due to a real effect or merely to random chance. It is widely applied in experimental research, agriculture, and psychology. One-way ANOVA is the simplest form, used when there is one categorical independent variable, factor, with three or more levels, groups, and one continuous dependent variable. For example, it can be used to compare the average test scores of students taught by three different teaching methods. The null hypothesis for one-way ANOVA states that all group means are equal, while the alternative hypothesis states that at least one group mean is different. If the ANOVA test yields a statistically significant result, It indicates that there is a difference somewhere among the group means, but it does not specify which particular groups differ. Post hoc tests, example Tukey's HSD, are then typically conducted to identify the specific pairs of groups that have significant differences, providing a more detailed understanding of the observed effects. Correlation analysis. Correlation analysis is a statistical method used to determine the strength and direction of a linear relationship between two continuous variables. It quantifies how closely two variables move together, but it does not imply causation. The correlation coefficient, typically denoted by R for Pearson's correlation, ranges from -1 to +1. A value as +1 indicates a perfect positive linear relationship, meaning as one variable increases, the other increases proportionally. A value of -1 indicates a perfect negative linear relationship, whereas one variable increases, the other decreases proportionally. A value of 0 suggests no linear relationship between the variables. Understanding correlation is crucial for identifying potential associations in data, guiding further investigation, and informing predictive models. Pearson's correlation coefficient is the most common measure suitable for interval or ratio data that are approximately normally distributed and have a linear relationship. It assesses the strength of the linear association between two variables. Spearman's rank correlation, on the other hand, is a non-parametric measure of the monotonic relationship between two variables, suitable for ordinal data or when the assumptions for Pearson's correlation are violated. Example, non-normal data, non-linear but monotonic relationship. Instead of using the raw data values, Spearman's correlation uses the ranks of the data points. Both coefficients provide valuable insights into how variables co-vary, but their appropriate use depends on the data's characteristics and the nature of the relationship being investigated. Visualizing these relationships with scatter plots is often the first step in correlation analysis, providing an intuitive understanding of the pattern. Simple linear regression. Simple linear regression is a statistical method used to model the linear relationship between two continuous variables, a dependent variable, response variable, and an independent variable, predictor variable. The primary goal is to predict the value of the dependent variable based on the value of the independent variable. This relationship is represented by a straight line, known as the regression line, which best fits the observed data points. The equation of this line is typically expressed as y equals a plus bx plus epsilon, where y is the dependent variable, x is the independent variable, a is the y-intercept, b is the slope, and epsilon represents the error term. Understanding this model allows for prediction and understanding of how changes in one variable are associated with changes in another. It is a foundational tool in predictive analytics and scientific research. Interpreting the coefficients in simple linear regression is crucial for understanding the model's implications. The y-intercept, a, represents the predicted value of the dependent variable when the independent variable is 0. However, its interpretation only makes sense if x equals 0 is a meaningful value within the context of the data. The slope, b, is the most important coefficient, indicating the average change in the dependent variable for a 1-unit increase in the independent variable. A positive slope suggests a positive relationship, while a negative slope indicates a negative relationship. The magnitude of the slope quantifies the strength of this effect. The R-squared value, another key metric, indicates the proportion of the variance in the dependent variable that can be explained by the independent variable. A higher R-squared suggests a better fit of the model to the data, implying that the independent variable is a good predictor. Multiple linear regression. Multiple linear regression extends simple linear regression by modeling the relationship between a single continuous dependent variable and two or more independent variables. This allows for a more comprehensive understanding of how multiple factors collectively influence an outcome. The model equation becomes y equals a plus b1x1 plus b2x2 plus bnxn plus epsilon, where y is the dependent variable. x1, x2, xn are the independent variables. A is the y-intercept. b1, b2, bn are the partial regression coefficients, and epsilon is the error term. Each partial regression coefficient, bi, represents the average change in y for a 1-unit increase in its corresponding independent variable, xi, while holding all other independent variables constant. This ability to control for other factors makes multiple regression a powerful tool for analyzing complex relationships in various fields. From economics to public health. Several assumptions underpin the validity of multiple linear regression, and diagnostic checks are essential to ensure the model's reliability. Key assumptions include linearity, a linear relationship between independent and dependent variables, independence of errors, residuals are not correlated, homoscedasticity, constant variance of residuals across all levels of predictors, and normality of residuals, errors are normally distributed. Additionally, multicollinearity, where independent variables are highly correlated with each other, can pose challenges, inflating standard errors and making coefficient interpretation difficult. Diagnostic plots, e.g., residual plots, QQ plots, and statistical tests are used to assess these assumptions. Addressing violations, perhaps through transformations or alternative models, is crucial for building a robust and interpretable multiple regression model, ensuring that the inferences drawn are statistically sound and meaningful. Non-parametric statistics. Non-parametric statistics are a branch of statistics that do not rely on specific assumptions about the distribution of the population data, particularly that the data comes from a normally distributed population. These methods are often used when data are ordinal, nominal, or when the sample size is small, and the underlying distribution is unknown or clearly non-normal. Unlike parametric tests, like t-tests or ANOVA, which require interval or ratio data and often assume normality, non-parametric tests work with ranks or signs of data rather than the raw values themselves. This flexibility makes them valuable tools when traditional parametric assumptions cannot be met, providing robust alternatives for hypothesis testing and inference. They are particularly useful in fields like social sciences, psychology, and medical research where data often do not conform to strict distributional assumptions. One common non-parametric test is the Mann-Whitney U-test, which is used to compare two independent groups when a dependent variable is ordinal or continuous, but not normally distributed. It is often considered the non-parametric alternative to the independent samples t-test. Instead of comparing means, the Mann-Whitney U-test compares the medians or ranks of the two groups to determine if there is a significant difference in their distributions. Other non-parametric tests include the Wilcoxon-signed rank test for paired samples, Kruskal-Wallis H-test for comparing three or more independent groups, an alternative to one-way ANOVA, and the chi-square tests for categorical data. Choosing the appropriate non-parametric test depends on the research question, the number of groups, and the nature of the data, ensuring valid statistical conclusions when parametric assumptions are violated. Time series analysis. Introduction. Time series analysis is a statistical technique used to analyze data points collected over a period of time, often at regular intervals. Unlike cross-sectional data, where observations are independent, time series data exhibits a natural temporal ordering, meaning that observations are typically dependent on previous observations. The primary goals of time series analysis include understanding the underlying forces that produced the observed data, forecasting future values, and identifying patterns or anomalies. This field is crucial in various domains such as finance, stock prices, meteorology, temperature readings, economics, GDP growth, and engineering, sensor data, where understanding temporal dynamics is paramount. It allows for the detection of trends, seasonality, and cyclical patterns that might otherwise be overlooked. Time series data typically comprises several components: trend, seasonality, cyclical, and irregular. The trend component represents the long-term increase or decrease in the data over time, indicating the overall direction of the series. Seasonality refers to predictable, repeating patterns or cycles that occur within a fixed period, such as daily, weekly, monthly, or yearly fluctuations. Example, retail sales peaking during holidays. The cyclical component describes patterns that are not fixed in duration, but tend to repeat over longer periods, often related to economic cycles. Finally, the irregular or random component accounts for unpredictable short-term fluctuations in the data that are not explained by the other components. Decomposing a time series into these components helps in understanding its structure and in building more accurate forecasting models. Smoothing techniques, such as moving averages, are often employed to reduce noise and highlight underlying trends and patterns in time series data, making it easier to analyze and interpret. Index numbers. Index numbers are statistical measures used to show changes in a variable or a group of variables over time relative to a base period. They are expressed as percentages or ratios, providing a simple way to compare magnitudes across different time points without dealing with large absolute numbers. Index numbers are widely used in economics and business to track inflation, measure economic growth, monitor stock market performance, and assess changes in production or consumption. They simplify complex data into easily understandable indicators, making it easier to identify trends and make comparisons. The base period is chosen as a reference point, and its index value is typically set to 100, allowing all subsequent values to be interpreted as a percentage change from that base. There are various types of index numbers, each with specific applications and calculation methods. The Laspeyres index measures the change in the price or quantity of a basket of goods and services using base period quantities or prices as weights. It tends to overestimate inflation because it does not account for changes in consumption patterns due to price changes. Conversely, the Pash index uses current period quantities or prices as weights, tending to underestimate inflation as it reflects current consumption patterns. Other indices include the Fisher's Ideal Index, which is the geometric mean of the Laspeyres and Pash indices, aiming to provide a more balanced measure. The choice of index number depends on the specific purpose of the analysis and the data available, as each method has its strengths and limitations in reflecting real-world changes. Understanding their construction and interpretation is crucial for accurately assessing economic and business trends. Statistical Software Introduction. The advent of powerful statistical software has revolutionized data analysis, making complex computations and visualizations accessible to a wider audience. These tools enable statisticians and researchers to efficiently manage, analyze, and interpret large datasets that would be impossible to handle manually. Popular statistical software packages include R, Python, with libraries like Pandas, NumPy, SciPy, and Matplotlib, and SPSS. Each software offers a unique set of features, programming paradigms, and community support, catering to different user preferences and analytical needs. Proficiency in at least one statistical software is now an essential skill for anyone working with data, as it streamlines the entire analytical workflow, from data cleaning to model building and reporting. R is an open-source programming language and environment specifically designed for statistical computing and graphics. It boasts a vast collection of packages for almost any statistical method imaginable, making it highly versatile for advanced research and custom analyses. Python, a general-purpose programming language, has become incredibly popular in data science due to its readability and powerful libraries that extend its capabilities to statistical analysis. Machine learning and data manipulation. SPSS, Statistical Package for the Social Sciences, is a commercial software known for its user-friendly graphical interface, making it particularly accessible for beginners and those in social sciences who prefer menu-driven operations over coding. Basic data import and manipulation are fundamental skills across all these platforms, involving tasks such as loading data files, cleaning missing values, transforming variables, and merging datasets. Mastering these foundational operations is the first step towards leveraging the full potential of statistical software for robust data analysis. Experimental design. Experimental design is a systematic approach to planning and conducting experiments to ensure that the data collected is relevant to the research question and allows for valid statistical inferences. The goal is to establish cause and effect relationships by manipulating one or more independent variables, factors, and observing their effect on a dependent variable, while controlling for other extraneous variables. A well-designed experiment minimizes bias, reduces variability, and increases the precision of the results, making the findings more reliable and generalizable. Key principles include randomization, replication, and blocking, which are essential for ensuring the validity and efficiency of the experimental process. Without careful design, even sophisticated statistical analyses can lead to misleading conclusions. Randomization is a fundamental principle in experimental design, involving the random assignment of experimental units, e.g., subjects, plots, to different treatment groups. This helps to ensure that groups are comparable at the outset, minimizing the influence of confounding variables and reducing bias. Replication involves repeating the experiment multiple times or applying treatments to multiple experimental units. This increases the precision of the estimates, allows for the estimation of experimental error, and enhances the generalizability of the findings. Blocking is a technique used to reduce variability by grouping experimental units that are similar with respect to an extraneous variable that might affect the outcome. For example, in an agricultural experiment, plots of land with similar soil conditions might be grouped into blocks. By accounting for known sources of variability, blocking makes the experiment more sensitive to the effects of the independent variables, leading to more accurate and powerful conclusions. Quality control statistics. Quality control statistics are a set of tools and methodologies used to monitor, control, and improve the quality of products and processes. The primary goal is to ensure that products or services consistently meet specified standards and to identify and address sources of variation. Statistical process control, SPC, is a key component, employing statistical methods to monitor and control a process to ensure that it operates at its full potential. By detecting deviations from expected performance, SPC helps prevent defects, reduce waste, and improve efficiency, leading to higher customer satisfaction and cost savings. These methods are indispensable in manufacturing, healthcare, and service industries where maintaining high quality is paramount. Control charts are the most widely used tool in SPC, providing a graphical representation of a process's performance over time. They consist of a central line representing the process average, an upper control limit, UCL, and a lower control limit, LCL. Data points are plotted over time, and if they fall outside the control limits or exhibit non-random patterns, it indicates that the process is out of statistical control, signaling a need for investigation and corrective action. X-bar charts monitor the mean of a process, while R charts monitor the range, variability of a process. Other charts include P charts for proportions of defective items and C charts for the number of defects. Process capability analysis assesses whether a process is capable of producing output that meets customer specifications. It compares the natural variability of a process to the specified tolerance limits. Providing metrics like CP and CPK, these tools collectively empower organizations to maintain consistent quality, identify areas for improvement, and make data-driven decisions to optimize their operations. Bayesian statistics concepts. Bayesian statistics is an approach to statistical inference that differs fundamentally from frequentist classical statistics by incorporating prior beliefs or knowledge into the analysis. It updates these prior beliefs with new evidence, data, to produce posterior probabilities, providing a more comprehensive and intuitive framework for understanding uncertainty. The core of Bayesian statistics is Bayes' theorem, which formally describes how to revise probabilities for a hypothesis when new evidence is obtained. This approach is particularly powerful when dealing with limited data, complex models, or when existing domain knowledge is valuable, allowing for more flexible and informative inferences. It is increasingly used in machine learning, medical diagnostics, and artificial intelligence. Bayes' theorem states that the posterior probability of a hypothesis H given observed data D is proportional to the likelihood of the data given the hypothesis, multiplied by the prior probability of the hypothesis. Mathematically, pH. D equals PD. H times P of H over P of D. The prior distribution represents our initial beliefs about the parameters before observing any data. It can be based on previous studies, expert opinion, or theoretical considerations. The likelihood function quantifies how well the observed data supports different parameter values. The posterior distribution, the output of Bayes' theorem, combines the prior information with the data's evidence, representing our updated beliefs about the parameters after observing the data. This iterative process of updating beliefs with new evidence is a hallmark of Bayesian inference, offering a powerful way to learn from data and quantify uncertainty in a coherent manner.